Okay, welcome back. Now I'm going to do a demonstration. I'm calling it Ballistic Pendulum. This is actually a very famous experiment that is done in a lot of colleges. You have a ball and then you compress it. There's a spring here, right? And then you shoot the spring, you release the spring, the ball goes and it hits the ground. And then from where it hits the ground, you can estimate what the initial velocity of the ball is. So from the range of the ball. So of course, in a laboratory experiment, you would do this over and over again, and you would get an approximate velocity for the V initial. I'm going to do it just one time, and then calculate the initial velocity of the ball. So what I'm going to do is first remove the pendulum portion of the experiment. So let's remove that. It looks like this. You can see here with a little hole. I'm going to press that hole against the pendulum. I'm going to press that hole against the gun right here, compress it. So I shoot this thing now. Okay, now I'm going to measure the distance of the bottom of the ball to the ground. From the bottom of the ball to the ground, this is the initial height. So I'm going to measure the distance from the where the ball is to the table. Okay, so that's about 4.5 centimeters plus 4.7 centimeters is 87.3 centimeters. So when the ball is released from the muzzle, the ball is here from the edge of the table to the ball. From the edge of the table to the ball is going to be 30 centimeters, right? Because the ball starts back here, then goes to the edge of the table, so that's 30 centimeters. Then I'm going to add that to the edge of the table to where it fell on the ground, okay? So the edge of the table is about here, okay? So then I just go down. This is 1 meter. Two meters, okay, 2 meters and 48 centimeters, so 2.48 meters. So now I have the height at 0.965 meters. I added the distance from the ground to the table, from the table to the bottom of the ball. I added up all those distances, I got 0.965 meters. The range, 2.48 meters from the edge of the table to where it hit, and then this 30 centimeters here, so I got the range is 2.78 meters. So how do I calculate the initial velocity from there? Well, since it's shot at horizontal, we have x is equal to v initial t, and then y final equals y initial plus v initial y t minus 4.9 t squared. This is the equations of projectile motion. But v initial y is 0, right? Because it's not shot upwards or downwards. So then I'm going to say x is equal to the range, which is r is equal to v initial t. And then I can say t is equal to r over v initial. And then y final is equal to 0 because it hits the ground. Y initial is the initial height. And then minus 4.9, right? So the y final is 0, initial height h initial minus 4.9, and then the t I can substitute range over v initial. Range over v initial quantity squared. Okay? So then, from there, I can calculate what the v initial is. Okay, so then I'm going to have here h initial is equal to 4.9 r over v initial squared. Then I'm going to say h initial over 4.9 is r over v initial squared, and then square root this, and then I'm going to get square root of h initial over 4.9 is equal to r over v initial, and therefore the equation is going to be v initial equals r times square root of, and then this one goes over to the other side, and then this one goes down to the bottom. So you're going to have 4.9 over h initial. So V initial is going to be, so now I'm going to put my range, 2.78 meters. Okay, then the initial height was 0.965 meters, so 6 meters per second. Of course, we only ran this one time, and I wasn't really careful about all the measurements. So this is a very approximate number. So then what's going to happen is I want to see, now that I know the approximate V initial, I want to shoot the pendulum into this hole here. And then, of course, the ball is going to come and hit this ball and go inside of it. It's going to be a perfectly inelastic collision, and the ball is going to go up and then eventually stop. So I want to be able to predict what the height of this is going to be, what the final angle is going to be, right? So I can make an equation and see if all the equations of momentum and collision work, okay? So this ball is going to come now, right? So let's draw a picture. This bottom is the most heavy portion, and it has a little orifice here where the ball goes and sits in there, right? And then they designed this so that this thing, as it goes up, there's a little wedge on the instrument there as it goes up, and then the grooves, it stops on those grooves. And then I can measure the final angle where it stopped. Okay, so we can practice that now. So I need to measure two of the masses very carefully, since I'm assuming that the mass of the rod is negligible compared to the thing. So then let me unscrew this, right? I'm going to measure this, and I'm going to measure the mass of the ball. And then we'll record that and then do our calculations. I measured the mass of the ball. I got 69.5 grams, and I measured the mass of this bottom portion of the pendulum, 234.5 grams. So let's estimate what's going to happen here. When this comes out, it's going to have a momentum, P initial, and then it gets embedded into this object. It has a final momentum. So the initial momentum is going to be its mass, 69.5 grams, times the velocity, which is 6.26, right? Then it gets embedded into that, so together they form a system, and then their combined mass is going to be 234.5 plus the 69.5 grams. Notice I didn't have to change from grams to kilograms, because if this is grams and this is grams, they cancel, and then I multiply this by V final, and then the final velocity comes out in the same units as the meter per second. So I don't need to change it. As long as this is grams and this is grams, I don't need to change to kilogram. So now let's calculate our estimate of what the final velocity of this is, V final, when. Then together, this system is going to go up, and I'm going to assume that the energy of the system after the collision is conserved. So in other words, the V final that it has after the ball gets embedded in there becomes its initial velocity. So that becomes its initial velocity of the next stage. So now it has kinetic energy, right? Together they have kinetic energy. That kinetic energy initial that they have will transform into potential energy by the time it goes up and stops. So potential energy final. So I'm going to assume that there is not much friction up here in the axle of the turn. So therefore the kinetic energy initial is equal to potential energy final. So what is the initial kinetic energy? 1/2 times the total mass of the system, because they're combined, times the V initial squared. That's equal to the potential energy. Okay, so the potential energy that it has here, it depends on the height, right? How high it goes up. So there's one other measurement I'm going to have to do. I'm going to have to measure the distance from the pivot point right here all the way to the center of this, right? All the way from the pivot to the center. So if I know that length, how do I calculate the height? So you do a little bit of math. You say here, okay, if the pendulum is like this, and this is, I'm assuming this is the center of the ball where it's resting, right, like that. So this is L, and then it finally goes up and then stops here, and this is theta, right? This is still L. So this component of the L, the whole thing is L. This component of the L is L cosine theta, right? L cosine theta, because it's the adjacent side. So if I take L and I subtract from there L cosine theta, right? Then I get this portion. L minus L cos theta then that's going to be this portion, and that portion is the height that it goes up. And so that's equal to h, right? So h is equal to L minus L cosine theta. So from here, I'm going to say the potential energy final is mg, and this is the total mass, m total, mg h final. The total mass cancels out, so I don't need the masses anymore. I only needed the masses in order to predict what the V final is going to be. So now the masses cancel out. So I have here half V initial squared G, and then H final is going to be this thing, which is just going to be L. So I can factor out the L. Then I can say 1 minus cosine theta. Right? Factor out the L completely. So what am I solving for? I'm solving for the angle that I predict. What angle will this rise to, right, until it stops? Measure the L, okay? It's going to be from here to here. So I put this next to the ruler. This is going to be my pivot point. I put the ruler at the pivot point at the 20 centimeter mark of the ruler. So from the 20, and then the center of this looks like it's about 50.5 centimeter right here. The center of the hole, approximately 50.5. So from 20 to 50.5 is 30.5 centimeters. Okay, 30.5 centimeter. So that's then I'm going to take the inverse cosine of that. Cosine inverse of 0.6579. And I get theta is 48.9 degrees. So I predict that this will go up all the way to 48.9 degrees. Okay, now if there's some friction involved in there, it's probably going to go up less than that, because the axle is going to stop it earlier than it should. And then there's of course other sources of error, because when I shoot the pendulum, when I shoot the ball, it might not always shoot consistently at the same velocity. It might shoot faster or slower. So there's all kinds of errors that could happen. Okay, so let's run it, measure the angle, and see what we get. Okay. Okay, and then now I have this device that it can be used to measure the angle. Right now it's showing you here 0 degrees, right? So if I put it on, if I tilt it like this, whatever angle it's showing you, that's going to be the angle. So you start out from 0 when it's horizontal. Okay, then I put it over here. It's about hovering around 48 degrees. So it's literally showing something like this. Okay, about 48 degrees. Yep, 48 degrees. Very close to our angle. And of course, we would run this several times and then run the projectile motion portion several times and then get a % error. But just running it once, gave us a good answer. Theta experimental, 48 degrees. So of course our % error is going to be 1.84% error. Of course you could multiply that by 100. So not bad for just doing it once, quickly measuring the height, quickly measuring the range, running this one time, measuring the L really quickly without doing really exact measurements. I get less than 5% error, less than 2% error even. Okay, so now you can see how you can use the ballistic pendulum equipment. You can run it, calculate the initial velocity, predict what the angle is going to be, and then compare the two and get a % error from that. And then you can prove the equations of momentum, kinetic energy, potential energy, and the equations of projectile motion all in one demonstration. Okay, thank you very much.